Good evening, everyone. My name is Stefan Wallentowitz, and I'm a professor at Munich University of Applied Sciences. I've been involved with RISC-V for a long time, but today I want to speak about a topic beyond RISC-V. It's about WebAssembly as managed runtime VM in embedded systems. VM is virtual machine here. So it's the concept of something that has run in the browser before, transferred to an entirely new domain, embedded systems. So let's have a look. What is WebAssembly? WebAssembly is an open standard for platform-independent bytecode, comparable to Java. It's also originally developed in this context around JavaScript to be run in browsers. So the idea was to accelerate and separate stuff that originally ran in JavaScript and run it in something called WebAssembly. It's roughly based on the LLVM intermediate representation, and so you can compile any LLVM supported language to WebAssembly. So this allows you to compile software for the browser, for example. And you can see many projects nowadays, even EDA tools that are compiled to WebAssembly and executed in browser. So it's very interesting. And also the concept of interpreted languages of platform-independent bytecode is not entirely new to embedded systems if you look back, for example, into smart cards. So generally, the first approach is to interpret such a language. So there's interpreters that can interpret WebAssembly code given in the form of bytecode or even in textual description. Those are the first idea that you would take for embedded system. But there's other options too, like ahead of time compilation, where you just compile your code from WebAssembly, from your original language, from WebAssembly, to the target platform and then run it on the embedded system. Or alternatively, do it just in time, which could be in the context of embedded systems a little bit challenging, depending on the resource constraints of your device. The whole idea of transferring WebAssembly into other domains is not entirely new. Especially in the context of servers or desktop computers, there's been a lot of work of transferring the concepts that you know, for example, from POSIX to WebAssembly. So for non-browser systems, you can use the so-called WebAssembly system interface, which is comparable to the POSIX interface in other languages, and use WebAssembly to access files, etc. So that's a great thing. Again, this is not really embedded systems in all circumstances, so that's one of the topics that I want to touch roughly later in this talk, how we need to tackle WebAssembly to have it ready for embedded systems. So now you might wonder, like, the whole story might be interesting already to you, but the whole concept of running something in a browser and deploying it to your large IoT deployment might be entirely different. What are the particular advantages for WebAssembly for embedded systems? Obviously, the first one is improved portability. You can even run new languages. You could introduce Rust in your code base and run this on legacy embedded devices for you, where, for example, don't have a Rust compiler at hand. So you could run Rust code, compile it to WebAssembly, and run it on some C platform that has a C-based WebAssembly interpreter. And you can switch, like, step by step your product development from C, C++ to Rust. I think this is a very interesting use case. Yeah, you can even link your WebAssembly code to your legacy C, C++ code. So there's even a transitional phase readily available with WebAssembly. You can also decouple languages. You can see at all the layers from the top to the bottom. You can decouple the languages from the frameworks that you want to use. You can have a Sapphire-based operating system running on an ESP, running an interpreter that, on the other hand, runs WebAssembly code that has been compiled from Rust or JavaScript. So it's very interesting. And obviously, and it's also like the origin of the whole idea of managed VMs, it provides very strong isolation properties, especially when we talk about the interpreted mode. So if you run it with an interpreter, as long as your interpreter is safe or secure, you already get very strong isolation properties. Beside that, like, basically you have isolation of the operating system from your WebAssembly applet, but you also have strong separation from WebAssembly's applets between each other. That's also one of the topics we see for the future for embedded systems, that we want to have the ability to split code into multiple applets and have isolation properties assigned to the communication between those applets. And finally, you have a very simplified update and migration. You don't need complex over-the-air methods that rely on static linkage or very specific code layout requirements, but instead you just update something in a flash. That's the idea. There's a couple of very popular WebAssembly runtimes, and I just highlighted the four most important ones. One is Webassembly, which doesn't support RISC-V at the moment. It's also not really in the context of bare metal. With bare metal, I mean something that doesn't require a standard library. And this is really just in time only, but it has VASI support. Then there's Wasmer, that's our favorite at the moment. It's Rust-based, it's target already at RISC-V. There's the no standard, which is a Rust thing, similar to what we call if you don't have a standard library. And it has ahead of time, just in time interpreter. So it's interesting for a couple of embedded systems, probably not your deeply embedded or smart card device. And it's also VASI compliant. So it's very interesting in the context that we speak about here. Then there's Wasmi, that's also Rust-based. That's the one that we currently focus on our work. It also has RISC-V support. It supports bare metal operation in Rust, and it's only based on interpreter. Doesn't have VASI compliance, which is also in many use cases not really necessary. And finally, there's the C favorite. There's many others in C, like Wasm3, for example. But the WebAssembly micro runtime also already has RISC-V support. It's very easy to use for bare metal usage, and it also supports ahead of time, just in time interpreter mode. That's something you definitely want to have a look in if you want to start with WebAssembly for your embedded systems. So what do we need? And that's what we are currently working on, and that's what I want to just roughly touch in this presentation. If we want some scalable WebAssembly infrastructure that we can use in vastly deployed embedded systems like IoT deployments, I think one of the things that we really need in the near future, and there's certain work in different projects, but there needs to be some kind of standardization in the terms of applet lifecycle management, for example. We need the concept of multiple applets, applet isolation, the management of multiple applets, and how to interact from the system and the applet in the entire lifecycle from incarnation to a termination of an applet. The other thing is remote applet installation. There's standards that you can find for concepts like in Java code, which could be generalized based on the global platform standardizations that could be of interest here. At the moment, our interpreters are all using custom implementations of this. Another topic that we started looking at, in particular in the concept of the frameworks of Swift and Spire, is the idea of authenticated communication. So that's another advantage if you run an interpreted environment or in this kind of managed VM. You could guarantee authenticated communication between applets and build these guarantees of the authentication in the runtime system and in the interaction of heterogeneous runtime systems too. And finally, I think this is something that we're already working on in different contexts. It's APIs and frameworks. So we need something like Arduino style programming, right? So you want to blink an LED, you want to interact with the physical environment, so you need access to the outside world. And the other thing is more complex APIs, like, as I said, like the global platform standards that we nowadays have for interaction with this kind of embedded platforms, more in the context of secure elements or smart cards, similar in TPMs, HSMs, etc. So what have we done so far? And that's always, as people that know me, there has to be a context to RISC-V in everything I do. So we started on a couple of RISC-V related prototypes. So the one that's most sophisticated at the moment, and I will talk about in the next slide, is the Wassmi runtime on the ESP, on the Espressif32 chip, which recently was launched with a RISC-V processor core in it. So this is a Rust-based runtime, in particular for IoT devices. Then we have the Wasm micro runtime on ESP32C3. That's a C-based runtime for IoT. Yeah, it's similar to Wasmi, but it's a little bit more accessible if you're not into Rust so much at the moment, while I strongly want to encourage you to have a deeper look into it. And finally, we have ported Wasm micro runtime on OpenTitan, which is a RISC-V based open source root of trust device. So this could be a C-based runtime for secure elements, HSM, etc. In future, we want to port Wasmi into TocOS, which is the favorite operating system of OpenTitan, so that you could use, similar to a smart card with the Java card environment on top, you could use OpenTitan with WebAssembly on top. So that's a project that we are currently working on. You can get in touch if you have interest in them, and we can cooperate on the integration with your environments if you're interested. So let's quickly touch the topic of the ESP32, sorry. So this is based on Rust and on the Wasmi interpreter, which is the Wasmi interpreter. So that's the currently the only Rust runtime that runs in this restricted no standard mode, which is like the bare metal environment for Rust. It doesn't at the moment support WASI, but as I said, like this is probably not in the range of what you usually want to have when you run a deeply embedded system. The good thing is that Rust already has full RISC-V support, so it is both for RV32 and RV64. Everything that's based on LLVM especially is very well supported, and there's a very strong commitment by Espressif to Rust. So what they're doing at the moment is that they port the Rust standard library to the open source ESP IDF, like the IoT development framework, which is their SDK. And they want to make it, I believe, in future like the primary or like first citizen at least of a programming environment for the ESP. And this is already well supported on the ESP32C3, which is the RISC-V CPU. There's a couple of shortcomings. It's a work in progress, and my bachelor student, Bastian Kersting, who graciously helped me with this presentation and with the work here, has been following it very closely along and running into issues that I believe are now at the stage that you can just quickly deploy Rust code to an ESP. And similarly, he has been able to deploy Wasmi on the ESP32. It's not yet able to run a full-fledged runtime like Wasma does. Wasma, as you know, like as I told before, has a little bit more support in terms of libraries, etc. But it's nearly there. There's another project we wanted to quickly highlight because that's one of the topics that we will tackle in the next couple of months. This is the idea of how to interact between applets and between the applet and the system. So the question is how you can generalize APIs and make them easier accessible from your applets and shared between platforms, right? So the idea is to have some kind of dynamic linkage later on, but at least some kind of static linkage against the specification. So the idea here, and this is vitix, is to define APIs in a DSL and a domain-specific language. This project originates from WASI, and the idea is that it's easier to grasp the API, especially if we're in the context of an environment that supports many high-level languages. The idea is that it's easier accessible than generic API via a well-defined DSL. And it motivates all the other tooling running upon of it. So there's a code generator for multiple languages, which generates C, Rust, assembly script code, etc., that you can then use to link against. And it generates runtime-specific code, which is at the moment, unfortunately, only supported in Runtime with a tool called Wiggle. We wanted to give you a quick shout out to the Rust Embedded HAL, the hardware abstraction layer. So the idea there, and this is the project that we also incorporated now, is to build a foundation for platform agnostic drivers. It defines types and traits, which is very interesting if you want to abstract a little bit in terms of interfaces. And it helps you like abstracting from the implementation of, for example, your UART. It's already implemented by many MCUs, for example, the High5, RISC-V, or the ESP-IDF IoT development framework. And this can also be used to define an API to WebAssembly, which is very interesting. I wanted to quickly, before I close this presentation, speak about another topic that's in the interest here of the RISC-V community. So the question is, what can we do in microarchitecture to support managed VMs? As you could guess, there's some drawback if you're running managed VMs in interpreted mode, for example. So whenever you want to access memory, you interpret this access, plus you need to manually check properties, etc. Of the memory system, because you can't always rely on the MMU. It depends on implementation, of course. And this is potentially part of the to be defined RISC-V extension, which is in early stages. If you have a look, like the hardware execution of bytecode has been there on the ARM platform, for example. There has been Giselle many years ago. There has been a successor to it, but it's discontinued in all platforms that I know of. So what you see, for example, is topics like pointer masking that you need for example, support garbage collection, etc. And all this stuff helps with the idea that the execution of memory access is very costly, and you can use this kind of memory tagging, for example, to allow direct memory accesses if your platform, for example, supports some specific understanding of the masked bits of the pointers. Similarly, I could think about ePMP, which has recently been a topic, or some kind of hardware firewalls that could be some very lightweight support for strong isolation properties in memory separation, maybe comparable a little bit to Trust Zone, but more sophisticated for MMU-less systems. And finally, what I personally want to look into, and this is a research topic I've set myself for the future, is the idea of instruction stream optimizations, but this is more maybe in software, maybe a little bit in hardware. I think primarily in software. In the interpreter, some kind of operation fusing. You could have a look. You could inspect some kind of GT behavior, where you observe the code at loading time or at runtime, and try to fuse different operations into one low-level operation, for example. So that's the roadmap. Currently, we work on the cross-platform integration, in particular on the WebAssembly deployment. So you could deploy the applets to multiple platforms, also spanning multiple platforms. Then the integration with the authenticated communication, like, for example, defined by SPIFFE, I think. We currently, at the low level, address problems concerning the WebAssembly binary size, both in Rust and in C++. We observe that there's some optimization potential. We want to further support more runtimes in the embedded space. We want to work together with the teams of the runtimes to support that. And we just started this very recently, just earlier this year, during summer. So please stay tuned and get in touch if you're interested. Thank you very much. Those are the ways you can access the demo, for example, on the ESP32C3 on the RISC-V platform. You can find the repository linked from there, from our GitHub repository. You can get in touch with me, stefan.wallentowitz@hm.edu, or with my bachelor student, Bastian Kersting@hm.edu, if you have any questions. Thank you very much, and enjoy the rest of the RISC-V Summit. Bye! Yes, hi everyone from the middle of the night in Munich, Germany. Thank you very much for listening. Do we have any questions? I'm just getting them from the chat. Yes, so there's one question. What would you suggest as a transition path from a legacy C stack? I think this is one of the most promising applications of the of a WebAssembly stack. Say you have a C stack. That's also a question that came up recently, that is not really strongly decoupled between operating system and applications, and everything's not messed up, and you want to have a transition into WebAssembly. And what I would personally suggest is looking into some lightweight assembler, WebAssembly interpreter like Webassembly, or if you wanted more feature complete, maybe the Webassembly micro runtime, and then just start picking the parts of your legacy C stack that you want to transition. There's an easy way of interfacing between WebAssembly and C and all of those interpreters, where you just have like tables that define symbols between both worlds, and you can switch in between. And I think it's a very smooth transition path. It's in general in early stages, I think, in terms of the overall platform. But if you're just looking at the application, I think that's a good start. There's another very obvious question, that is, what is the performance impact of interpretation, which is always, of course, the obvious negative part of interpreted languages. So I don't have the numbers at hand. We've seen some ahead of time impact already in the area of 30 to 50%. Interpretation generally is more in the axis, so it's more like multiple 100%. We'll have a look into it. I don't believe in JIT, and I think there's some security implications in AOT, but it could be of very interest to see what to do with hardware strong isolation properties, for example, that can help here. There's another question. When can we expect a multi-device demo? Yeah, that's what I'm currently working on. It's around the corner. We currently focus on the Expressive board, which is a very, very nice board. Currently, we work a little bit on integration of APIs to the cryptographic accelerators in the ESP to use them from the applets, and then we build like an end-to-end, starting from your AWS or whatever, your cloud, your edge device, your IoT device, and your root of trust, and all of them can run the same applets, and they can, in an authenticated way, communicate with each other. And then there's another one that is, why did you pick Rust? Which is, of course, an obvious question always. It's still for embedded. I think the support for Rust is in the toddler phase, probably. It's not still there where you would expect it to be compared to mature C environments that you use in your project. But it's getting better. And we have, that was maybe also the major pain point if you look at the Rust-based WebAssembly interpreters. They use a lot of external dependencies, and in general, there's an embedded dependency that you don't rely on a standard library, which is no standard stuff in Rust. And it's really hard to navigate if you want to use something mixed. Expressive, again, great shout out to the team at Expressive. They are working on an approach that could probably scale out for embedded systems in general in the future. So that's very interesting to follow. I think it's a very good time to enter the space, and I would encourage you to get in touch. I wrote my email in the chat. Just drop me an email if you're interested in more details or want to discuss. Thank you very much. Have a great evening, I think, for you. I will go to bed, and see you next year at the RISC-V Summit. Bye.